All right, so we are now ready to start talking about what this number e does for us. We'll look at a couple of situations in this section, and as you go on in math, you'll actually see e more and more. We'll start with an application to finance. When you invest money, you know that you earn interest on that investment, and there are actually a couple of different equations that govern this. Typically, when we have compound interest, interest is paid into our account at specific times while the money is invested. And once that interest is deposited, you earn interest on the interest. That's what compound interest really is. Here is the equation that governs compound interest. P times 1 plus r over n to the nt. And there's a bit of an error here. It says APRT is defined above, but there is no above, so let's do it right now. P is the principal, how much you invested. R is the interest rate. It does have to be expressed as a decimal. T is the time, usually in years when we talk about interest. And then as they told us, N is the number of times per year the interest is compounded. I guess I skipped A. A is the amount in the account. Squeeze that in there. All right, so that's what happens when we have compound interest. I'm going to come back to this in just a minute because the first few examples we'll do in example 1 refer to this equation. So let's go ahead and practice using that a little bit. We're going to invest $8,000 in an account advertising an APR, or annual percentage rate, of 5%. We'll leave the money in the account for 3 years. How much will be in the account if we compound our interest quarterly? All right, so let's make a list of PR, T, and N. The principal is going to be the $8,000, the amount we invested. The interest rate was 5%, so we'll use 0.05, the decimal form of that. The time, 3 years. And N, if we're compounding quarterly, that's 4 times per year. So the amount in the account, if I substitute into my equation, will be 8,000 times 1 plus 0.05 over 4 raised to the 4 times 3 power. And if I plug that into my calculator, let's see, 4 times 3 would be the 12th power. I am getting a value of $9,286.04. Makes sense to round to 2 decimal places since we're talking about money. All right, what happens if we compound more often? Same everything else, so P, R, and T won't change, but we want to compound monthly. So this time we'll use an N of 12 times a year. So my principal is still 8,000, and then I have 1 plus, R is 0.05, N is now 12. The exponent is NT, so 12 times 4. Or 12 times 3, I'm sorry, T is 3. So I've got my 8,000 times 1 plus 0.05 over 12 raised to the 12 times 3, or 36th power. $9,291.78. So you can see what happened when we compound more often. we actually end up with more money in the account. That's because we're getting our interest sooner and beginning to earn interest on that interest more quickly. All right, what about if we compound daily? If we compound daily, n is 365. We'll assume we're not necessarily in a leap year. So one more time, let's write out our equation. Interest rate hasn't changed, but our n is now 365. So now I have $9,294.58. And once again, notice we're compounding more often. We end up with more money in the account. Now, I'm going to admit this is probably more mathematically interesting than anything else, because if you're sitting there thinking, gosh, you're making a lot of fuss over $3 over 3 years, probably true. But it's the interest is really in the mathematical function. And the question I'd now like to ask is, what's the best we could do? How often could we compound the interest in order to make our total after 3 years as large as possible? Could we do it every hour instead of every day? What about every minute or every second? In fact, there's something called compounding continuously, and that's going to always give us the maximum yield at the end of our time period. Continuously compounded interest can only be calculated using the new number e that we've been working with. To find continuously compounded interest, we take p times e to the rt. So let's try that here. We still have that $8,000 investment. Our interest rate was 5% or 0.05. And we're doing this for a time period of 3 years. And we get $9,294.67. So as you can see, compounding continuously gained us a whole 9 cents over compounding daily. But this is the maximum amount that we could ever get. And that's what that number E does for us in this particular application. All right, we'll look at a couple of other financial. Oh, actually, I guess we're continuing to go on with this problem just a little bit more first. So instead of advertising the APR, annual percentage rate, banks usually advertise the APY, which is what's called the annual percentage yield, defined as the percent return on the deposit after 1 year. Let's go ahead and calculate the APY in the account, assuming interest is compounded continuously. So we started with our $8,000. We're looking at return on the deposit after 1 year. So that would mean that even though my principal remains $8,000 and my rate is still 0.05, I now want to do a time period of just 1 year. So A equals PE to the RT would be 8,000 e to the 0.05 times 1. Is $8,410.17. In order to figure out the return on the investment, or the percentage that the money has gone up, I actually have to compare these two values. you can see that we've gained $410.17. And if I divide that by what I started with, the $8,000, I get 0.0513 approximately, or 5.13% APY. That's the percent that my money increased by over the course of 1 year. You can see why banks would rather advertise the APY. The continuous interest rate, 5%, doesn't sound quite as good as the APY. That's always going to be a little bit higher. And considering this, the relationship between our exponential growth models, AE to the KT and AB to the T, the continuous growth constant is always going to sound like a little bit smaller than the growth constant that we're going to get from B. And that's because B is an annual growth rate. All right, we'll continue to use our new equation, PE to the RT, to solve a couple more problems. In example 2, Sue and Bill received a large inheritance. They have a newborn baby and decide to invest part of the money in a college fund for their child. They'd like to have $80,000 in the account by the time the child is 18 years old. How much must they invest now if the account pays 6% interest, compounded continuously? So once again, let's make a list of everything we know. Let's see. Their goal is to have $80,000 in the account. So the amount at the end is supposed to be $80,000. How much they have to invest now, the principal, is unknown. The interest rate is 6% or 0.06, and they have 18 years. So time is 18. So if I substitute all of that information into my continuously compounding interest formula, A is the 80,000, P is still unknown, and I'd have e to the 0.06 times 18. E to the 0.06 times 18 is about 2.945. There's that P. Again, I'll keep all the digits in my calculator so that I can use them in a minute, because I'll have to divide by that 2.945. Divide by the previous answer, and it looks like $27,167.64 is what they would need to invest now to achieve that goal. All right, we have one more financial application. In example 3, we have $3,000 invested in an account paying 8% interest. How long will it take the money to double? First, if interest is compounded quarterly, and then if it's compounded continuously. So let's see, our list of information. This is a quarterly compounding, so we'll have an N in this problem. We start with $3,000, and we want the money to double, so we want to end with $6,000. The interest rate 8% or 0.08. Time we don't know. How long will it take? But if interest is compounded quarterly, n is 4. So I'm going to go back to my compound interest formula and plug in everything I know. With a t being our unknown here. Let's simplify inside the parentheses a little bit. Let's see, that would be 0.02 plus the 1 would be 1.02 to the 4t power. There's my exponential that I need to isolate. So we'll divide by the 3,000. We get 2 equals 1.02 to the 4t. I need to get at that t, so to get rid of the exponential, I'll use a log base 1.02. Exponential and log with the same base are inverse functions. And looks like just about 35. 35.003 would equal 4t. And if we divide by 4, it's about 8.75. So about 8.75 years to double the money. One thing to perhaps consider, did it really matter how much we invested? Let's say we had invested $10,000 and we wanted to double the money. Well, that would have made that $20,000. If that was $20,000 and that was $10,000, when I divide here, I'm still going to get 2. So if you want to double the money, it really doesn't matter how much you start with. You're going to end up with the same amount of time. All right, let's redo the same problem, but this time assume that the interest is compounded continuously. We know that's a little better for us, so we really ought to reach our goal a little bit faster. Let's find out. A equals P, e to the RT. Again, A is 6,000, P is 3,000, and then I would have e to the 0.08t. Dividing both sides by the 3,000 gives me 2 again. And then I need to get rid of the e. Exponential base e, the inverse would be the natural logarithm. So we'll take the natural log on both sides. The inverses work here. So the natural log of 2 is equal to 0.08t. And if I divide both sides by the 0.08, I have about 8.66 years. So indeed, notice that continuously compounding interest is a little bit better for us. We were able to reach the goal a little bit faster. All right, that's the end of Part B.